So electrolysis of other molten substances, just like we studied yesterday or the day before yesterday, that it's pretty easy if you study a substance, the formula is right in front of you, and you always know that the metals are put first and the non-metals are put after in a formula, and the metal always forms the positive ion and the non-metal always forms the negative ion. From the formula, you can of course perceive what charges do they have. I also explained that if this positive it has a single positive charge, then it would only accept an electron and become a neutral atom, and that this whole process would occur at cathode for the metal, and this would be known as reduction since it's a gain of electron. So that's the half ionic equation for it right there, and the name of the process as well. Now, moving on, for the non-metal, for chloride ions, since they have extra electrons already from the ionic bonding, they are going to lose those electrons and they are going to be converted into chlorine molecules by the process of oxidation occurring at anode. So I hope all of this should be easier for you now, right?
Yeah.
Okay. Although this is easier, but what you need to understand and what's not written over here, but was given in the previous pages of the book, are the observations. So now you need to understand, if this, let's suppose, is the cathode, the sodium is going to deposit on the sides. And what would be the observation? Sodium is a metal of silver gray appearance. So you usually write silver gray metal deposited on cathode. That's not written anywhere over here, but since we have previously studied what the observations look like, so you should be able to come up with the observations for both cathode and anode. So if we talk about anode, let's suppose this is anode, and I'm going to write an A for the ease. You should know that there would be bubbles over here, and this hole will be covered in a cloud of gas, and it would be pale green gas bubbles, right? So
Yeah,
we
understood.
should be able to come up with the observations for whatever is forming at the cathode or the anode. Most of the time, they are the simplest metals and non-metals. Since all the metals are of silver gray color, except for copper and gold. Copper is red-brown, gold is golden in color. So it's pretty easy for the rest of the metals. You simply write silver gray metal deposited, whichever metal is that. There are only two exceptions for it, right? And for the case of non-metals, it gets a little tricky. Since fluorine, chlorine, bromine are gases, iodine most of the time becomes a solid, and sulfur, oxygen, nitrogen, hydrogen, not hydrogen, of course, it does not go to anode in that case. So they have different appearances. Well, when we talk about nitrogen and oxygen, they are colorless gases. When we talk about fluorine, chlorine, and bromine, they're colored gases. So you should be able to remember how you are going to mention them, right? Now,
Yeah.
in the case of equations, remember we wrote these twos in order to balance the equations. Now, these half equations are ionic equations. They consist of ion, they consist of compounds as well. So you must always balance in terms of number of atoms on both sides, but also in terms of charges. Now, let's take a look what they mean from in terms of charges for cathode. Now, the charge on this one is +1. Then we have this plus sign right over here. Then the charge on electron is -1. And the charge on an atom is always taken as 0 since it's neutral. So the overall charge on left and right is equal. For anode, it becomes a little tricky, but still is easy if you understand it and practice it a couple of times. This is number 2, this is -1, so it's 2 into -1 on this side. And on the other side, since this is a proper molecule, neutral, it's 0. And we have 2 into -1 on this side and this plus sign. So exactly we have -2 on one side and -2 on the other. So yeah, In both the cases, the number of atoms as well as the number of charges on both sides of the equations are balanced. That's another good way to recheck whether the half equation you have written was correct or not. And he explained the same thing in the upcoming lines. Now, if we're clear with the example of sodium chloride as a molten substance, can we move on to aluminum oxide?
Yeah.
Good. So moving on to aluminum oxide. Aluminum oxide is a little different since the formula consists of numbers. Aluminum, there are 2 atoms of aluminum and 3 atoms of oxygen in one empirical formula for an aluminum oxide. Now, we get aluminum at the cathode since it's a metal and it's written on the left-hand side in the formula. Oxygen at the anode since it's a non-metal and written on the right-hand side of the formula. Now, if we work out their charges and reverse cross multiply, would understand that aluminum is +3 and oxygen is -2. Whether you write it like this or you write it like this, both ways it is correct. But I do tell my students that keep one thing in mind. If you're writing like this, write it like this throughout your paper. If you're writing like this, write it like this throughout your paper. Do not keep changing the symbols. That doesn't look good on your paper. And by the way, your book opts this, so I would rather say that you opt this too, right? Okay, so getting back to it, now since this is +3, and I told you yesterday adding 3 electrons would make it neutral, so that's the half reaction on the cathode. And again, a silver gray metal deposited on the cathode. Now, he explained the whole thing in terms of charges again. Now, this is +3 and then plus sign, and then we have, my bad, 3 into -1, and then the arrow sign, and aluminum is neutral, so this is 0. So 3 minus 3 is equal to 0, and the same thing is mentioned over here, right? So the charge is also balanced along with the number of atoms. If we look at the anode, and I'm going to move forward, it's a little tricky, but we did that equation yesterday. So I hope you understand that 2 oxide ions are going to give out 4 electrons as a part of oxidation reduction. Losing the electrons will give us molecular oxygen as a neutral species in the product. So since each oxide ion has 2 extra electrons and oxygen goes around in pairs, so we must remove 4 electrons to form an oxygen molecule. So that's how it works. Let's go with the charges. 2 into -2 on this side, moving on 0 for the neutral molecule, plus 4 into -1 on this side, right? So it's actually -4 on one side of the arrow and -4 on the other side of the arrow. So yeah, the charges are balanced for this oxidation reaction as well. I hope that makes sense, right?
Yeah.
Good. Moving on, the next example is zinc chloride. We needed to take an example out of the transition elements in order to make sure that you understand it. So that's a very good way for the book to take the example of zinc chloride, since the formula is ZnCl2. And even if you don't have the formula, you have a name, you know that the oxidation state on zinc is +2. From this name, or from this number, you'd get the same thing. So that's +2, added 2 electrons. We get neutral zinc as a reduction reaction on cathode. And on the anode, since we're already familiar with the chloride reaction from the sodium chloride example, so it remains the same, which gives you an idea that chloride ions every time are going to give the same chloride reaction, no matter whether they were a part of zinc chloride, or they were a part of sodium chloride, or they were a part of magnesium chloride. The reaction remains the same. So that's an easy part. If you're familiar with most of the metals and non-metals during practice, you're not going to find their reactions difficult in the actual paper. Now, there are a couple of things we need to note and we must know. Number one, first hint, the common mistake is to put the electrons on the wrong side of the half equation. Now, remember, we have been doing one single thing over and over again. In reduction reactions, we have been writing electrons on the left, and in oxidation reactions, we have been writing electrons on the right-hand side. So make sure you do not write them on the other side. So for every type of reaction, remember the same happens. Since we have already generalized that in case of cathode, it's reduction, so the electrons are always going to be on the left of the equation. And at anode, oxidation happens, so the electrons are always going to be the right-hand side of the equation. So another hint, as a good way of remembering an ox red cat or an oil rig cat, so oxidation, reduction reactions can be understood in the similar way, right? Cathode, anode, oxidation, reduction, correlating this one with this one and this one with this one can be remembered by this, right? So other generalizations, if you electrolyze a molten ionic compound, only two elements, you'll get the metal at the cathode because metal form positive ions, non-metal at the anode because non-metal forms negative ions. But there is an if it consists of two elements. And most of the examples that you're going to cater for molten compounds are with two elements. Means I hardly or can rarely find an example with three elements for molten compounds in past 10 years papers. At least I haven't seen any. So rare is not even the right word to use over here. I can safely say never. Okay. Coming to the second generalization, reduction always occurs at the cathode, oxidation always occur at the anode. This was the hint was all about. So you already know that. We also know positive ions are cations because they are attracted to cathode, and negative ions are anions because they are attracted to anode. Now you understand that cat of cations and ions, the word ions has the starting part coming from the electrode cathode, and an starting part of ions has this word an coming from anode. And the word part electrode is actually coming out of ode, electrode. So yeah, the names are given in such a way that the students have an ease memorizing it. Okay, so let's move on. I hope all of this is clear, right?
Yeah, this makes sense. I might not be responding a lot because I'm writing it down. But I'm understanding. So
Okay, so are you done writing?
yes, I'm done.
Okay, good, good. So I'm going to clear it up and I'm going to move forward. Okay, so since I was talking about with two or three elements, so there are a few things that we need to understand. Not all ionic compounds can be electrolyzed when they're molten. Some may break up into simpler substances even before their melting point. For example, copper to carbonate breaks into copper to oxide and carbon dioxide even on Jelton heating. So it's impossible to melt it. So there can be an exception. This is the only exception your book covers. So memorize the exception. So if there is a question about it, you would know. And that's the only one in there.
Yeah.
Moving on, electrolysis of aqueous solutions. Now, the aqueous solutions are electrolyzed in the similar way. The chemistry behind it is not the same. So molten electrolysis for molten salts or electrolysis for aqueous solutions of salts are different. Why are they different? Let me clarify. Now, if we're going to put sodium chloride in water, and if we are going to pass electricity through it, you obviously understand that this is going to break down into sodium ions and chloride ions. Water is a covalent compound, but when electricity is passed through it in the presence of some ions, the problem is water starts breaking down into ions too. Although this is a covalent compound, it shouldn't be showing this property, but it does. And it breaks down into H positive and OH negative ions, which actually brings a little bit of the change to the whole process. Now, previously, you were having one cation, which was going towards the cathode, and it was pretty easy. And you had one anion, which was going towards the anode, and it was pretty easy to write its equation. But now, that's not the same. Now, notice that if I mark cations with a blue color, then you have two cations. And if I mark anions with a red color, then you have two anions. And You already probably know that if for a single person, if you have something that you need to consume, or if you have some place to get to, for a single person, it would be not be a problem. But if two people are trying to reach the same goal, it might turn into a competition. So getting to the respective electrodes, although this doesn't occur in the same way, but for the understanding of the student, or to make it easier for the student, to make it more attractive and learnable for the student, I tend to say that the cations and anions start competing with one another in order to get to the electrode. So now we have two cations, and of course they're going to compete for the electrode, and one of them is going to win, one of them is going to lose. When I use the word win, I actually am talking about the ion that is successful in reaching the cathode, or in case of anions, the ion that is successful in reaching the anode. And when I'm using the word lose, I'm trying to say the one that stays inside the solution and is not able to get to the electrode, and the other one wins. So if we go with this, what happens is that sodium and hydrogen are competing with one another. So when sodium ions and hydrogen ions are competing with one another, what happens that out of these, hydrogen ion wins, it goes to the cathode, and it forms hydrogen gas over there. Like all other nonmetals do, they stick in pairs. Hydrogen is also a nonmetal. Even when it goes to cathode, it sticks in pairs in the form of hydrogen molecules. When it comes to the competition between chloride ions and hydroxide ions, actually one of them can reach the anode, and that really depends upon the concentration to answer. So how do I know that out of these, this one is going to win? And how do I know that out of these, whoever is in the more concentration gets to win? Why not the concentration part over here? Which brings us to a few specific set of rules. What you're going to do every time for a solution is that you're going to consider the salt in water. Whatever the positive ion is, he's up against hydrogen ions. Since water is every time going to split into the same set of ions. Whatever the negative ion is from the salt, he is up against hydroxide ion, OH negative. So in that trace, I'm going to give you a few set of rules to know which cation or which anion is going to win. All right. And for that, we are going to go with a couple of investigations first. Okay. Now, a practical investigation in which we're going to investigate the electrolysis of an aqueous solution. Before we get started, always wear eye protection. Do not smell chlorine, especially if you have asthma. Once chlorine is detected, the current must be switched off. All right. This is for the safety, since chlorine is poisonous. Right. So we took a sodium chloride solution. You'd see that we have a specific way of doing it. Now I'm going to clear a few parts of the apparatus before I move on to the procedure. So you see the battery on one side and how it is connected to the electrodes. The electrodes are actually going through the holes pierced into the carbon in the whole rubber bung, and that is connected to a proper glass tube in which we have poured the concentrated sodium chloride solution. And then we have the test tubes or the boiling tubes, which are inverted on top of those electrodes. All right. So why do we do it like this? We do it like this so that when these electrodes are about to produce some gases, the gases would be collected on the top of this test tube, and the gases will not be escaping into the environment. Since we were talking about sodium chloride, and we already know in case of chloride, there is a good possibility of producing chlorine. And since chlorine is poisonous, so that's why we are going with such kind of apparatus settings. I hope you understand this way. The chlorine will not be allowed to leave the test tube, and that way the poisonous chlorine is not going to affect the person who is going to perform the experiment, right?
Yeah.
So if you're supposed to draw a diagram, you must look at the substance first, And if you think it's going to produce a toxic halogen, a poisonous halogen, like fluorine, fluorine, or bromine, then always draw the diagram like this. Do not draw any other diagrams that we have previously seen, right? For example, let me take you a little bit back to the place where we had the diagram. Where is it? Yeah, this one. You cannot draw an open diagram like this one if it comes as a part of the exam. They tried to show you the apparatus, but as soon as you are supposed to perform it at school or in a lab, then you must know that for bromine or fluorine or fluorine, since they're all poisonous, we're going to draw that diagram and not this one. All right. So that's why I wanted you to see the difference between the two and know which one you need to draw if that comes as a part of the question, although that is a very rare in Edexcel exams, but still, if that comes as a part of the question, you should know how to cater it. Now let's go with the procedure. Set up the apparatus as shown, glass tube, rubber bung, electrodes. This is all as a whole known as an electrolytic cell. Now pour concentrated sodium chloride solution. Sometimes we use the word concentrated. Sometimes you're going to see the word saturated over there. Whether you see the word saturated or whether you see the word concentrated, it means the same thing. That means a good amount of salt has been dissolved into water before it was being poured over here in the glass tube, right? And this concentrated is actually a very good word in terms of solving which ion is going to go to the specific electrode, since I also already told you that the concentration matters. So whether the word concentrated is written over here or the word dilute is written over here, that is really going to affect the outcome of electrolysis. So you should always look out for this word as a part of the question. All right, how it's going to affect the outcome, I'll explain a little later as soon as we're done with the process. So let's move on to the next step. Place a test tube containing sodium chloride solution over each electrode. The test tubes must not completely cover the electrodes or the ions will be unable to flow and there would be no current. So you'd notice there is, of course, some space over here, here, or here, right? Now, you might not be asked in the paper to draw a diagram, but you might be given with the diagram and you need to find a mistake in it. This is a very clever way of, if the test tube is put all the way over here and there is no space to leave the system, of course, the current won't be able to flow because the ions inside the test tubes won't be able to move freely. This doesn't complete the circuit and the current won't flow, the electrolysis won't occur. So they cleverly draw this close, not close, and in fact touching the rubber band. And if that happens, that's the biggest mistake in the structure and the whole apparatus setup. So keep that in mind as a question related to pointing out mistakes in the diagram. Moving on, connect the battery or the power pack to the electrodes. The experiment should be done in a fume cupboard or fume hood or in a very well ventilated room because chlorine gas is poisonous. Also, since the hint is mentioned over here, we do tell the students, if you perform this experiment, as soon as you can see the pale green gas or you see the bubbles, do not keep the switch open for a longer duration of time. When you detect it, be the switch open for a few seconds, maybe a minute, maybe a couple of minutes, and that's about it. Turn off the switch before the chlorine starts becoming dense over there in a good amount of bubbles. In that case, if the room is not well ventilated, it is definitely going to affect your breathing. Since it's poisonous, it can easily take a person to a hospital or even kill, right? So that's why the whole set of instruction. Now, if we see any bubbles or gas or a metal forming or getting deposited at electrodes, the gases can be tested. That part is covered in chapter 18. Now, in this specific experiment, we see bubbles of gases at both electrodes. When the gases are tested, we find that hydrogen forms at negative electrode and chlorine forms at the positive electrode, respectively, cathode and anode. All right. So we would expect to get the same volume of hydrogen as chlorine. However, in reality, we appear to obtain less chlorine than expected because it is more soluble in water. Again, a point which will be covered in chapter number 18. So although it's written over here, but we are going to cover it in chapter 18. And there I'm going to discuss which one's soluble and which one's not, and how it's going to affect the outcomes of or the appearance of apparatus setup in electrolysis. Moving on, if we are talking about the electrolysis of sodium chloride, what happens is that at anode we get chlorine, at cathode we get sodium in case of molten sodium chloride. But when you go for electrolysis of sodium chloride solution, you don't get the same products. The hydrogen is something that comes out of the cathode instead of sodium. Water is a weak electrolyte. It ionizes very slightly to give hydrogen ions and hydroxide ions. Whenever you have water present, you have to consider these ions as well as the ions of the compound that you are electrolyzing. So what exactly happens at cathode? Let's discuss the reasons why we are getting hydrogen gas at cathode and not sodium deposited. The details are that the solution consists of both the ions. They are both attracted to the negative electrode. However, sodium is a very reactive metal. This means it's very difficult to add an electron to sodium ion to convert it back into a sodium atom. Hydrogen, on the other hand, is less reactive than sodium. So it is easy to add an electron to a hydrogen ion to form a sodium hydrogen atom. But hydrogen atom combines in pairs and form a hydrogen molecule. So remember, hydrogen ion comes from water splitting up. So each time a water molecule ionizes, it also produces a hydroxide ion. So actually, we have a buildup of both hydrogen ions and hydrogen oxide ions around the cathode. These hydrogen oxide ions make the solution alkaline in the region around the cathode. Now we're going to explain all of these since I've explained a couple of things together at the same time. So I'm going to bifurcate it with the help of different diagrams. The first diagram, figure 10.7, tells us that the water was bifurcated into or divided or ionized into hydrogen ions and hydroxide ions. Now, hydrogen ions discharge as hydrogen atoms, after which they are converted into hydrogen molecules at the cathode. Hydroxide ions, however, go for a buildup around the cathode. Now, remember, there were some sodium ions also getting attracted to the cathode. This is positive, this is negative. They are both going to react with one another around the cathode, and they're going to form a sodium hydroxide solution, which we're going to study a little later. So I'm going to move on. There is alternative way of looking at the cathode reaction, starting from neutral water molecules. When they get electrons, they're converted into hydrogen gas and hydroxide ions. Now, in this case, the solution becomes alkaline on the side of cathode since hydroxide ions are produced. Hydroxide ions are alkaline in nature and they can easily turn red litmus paper into blue. That is something that we usually cover in the next part of this book. I mean, not in principles of chemistry. We usually cover that in inorganic chemistry. So you'll get to learn that in the part of acids and bases chapter, hopefully. Even if you don't understand it right here, don't worry. We're going to consider these parts later. So at the anode, chloride ions and hydroxide ions are both attracted by the positive anode. This is slightly easier to remove electrons or oxidize the hydroxide ion than from the chloride ion, but there isn't much difference. There are, however, many more chloride ions present in the solution. So it is mainly these that they are oxidized at anode. What does this line mean? I hope you remember that I was telling you that concentration matters. And when we are using the word concentrated before the formula or the name sodium chloride, that means there would be huge amount of sodium ions and chloride ions forming out of this system. So which means if in comparison, these or these, which one will be more in the system? Of course, it's a concentrated solution and these will be more in amount. And if they are more in amount, they are concentrated, they are going to get electrolyzed at the anode. Then, is there a chance that this gets electrolyzed at anode? Yes, there is. if the concentrated word was not mentioned over there and the word dilute was mentioned over there, which means less amount of salt and more amount of water is present, and more amount of water means more amount of hydroxide, which means this won't electrolyze at the anode. In fact, this one does. Hydroxide does. So where is the equation of hydroxide? You'd find it over here. If the sodium chloride solution is dilute, you'll get noticeable amounts of oxygen produced as well as a little amount of chlorine. This comes from hydroxide ions since they are converted back into water and oxygen, giving us few electrons. But it is unlikely you'll be asked about this in international GCSE. Well, I tend to ask my students, if you're going to remember this equation, this is really going to help you in A levels, if not IGCSE. All right. So now we know for a salt, in case concentrated is written, this is your product. In case dilute is written, this is your product. Make sense?
Yes. Wait. Yeah. Okay. I'm done writing. Yeah. Makes sense.
Okay. So the remaining solution, if the electrolysis is carried out for a long time, we can work out what the final solution remaining at the end of entire process would be. Since this goes out to anode and this goes out to cathode, we are left with a buildup of these two ions and they will form hydroxide solution, just like I told you on the previous page. Since they have different charges, they can get attracted to one another and form a solution. Make sense?
Yeah. Yeah. It makes sense. Yeah.
Okay. Now I'm going to revise it or I'm going to give you a whole recap. Since getting all of these on a single page is a little, it wasn't given on a single page, so I'm going to give you a recap. So we started off from this, and from this, as soon as it dissolves into water, it is converted or ionized into two different ions. As soon as we start passing the electricity, water is also bifurcated into two ions. Now, for the process between this one, more reactive. Now I'm writing the reasons so that it would be easier for you to remember. So stays in solution. More reactive does not like to move. Since they are more reactive and they can react with anything present around, so they are not interested to leave the solution. So this one is less reactive. So this one really goes to cathode, right? In case of chloride ions versus hydroxide ions, in case of concentrated solution, this goes to anode. In case of dilute solution, this goes to anode. Actually, this extension work does tell us that sometimes both the ions are able to go to the anode and little amount of one and more amount of the other is produced. In case of concentrated, most of the amount of chlorine is produced, but a little amount of oxygen is produced. In case of dilute, more amount of oxygen is produced from this reaction from hydroxide, and a little amount of chlorine is also produced. So in reality, actually, some of the ions from the counterpart or the competitor is also capable of getting towards the electrode and going out in the form of their neutral molecules, or whatever is the product at that specific electrode. Now, this is a whole summary in case of solutions. So what does this summary tells us? This summary tells us that reactivity matters among cations, but concentration matters among anions. Reactivity does matter among anions too, but right now in our plate, we are only dealing with concentration. We'll discuss the reactivity a little later for anions as well, one step at a time.
Okay.
If you're done writing, can we move on?
Yeah, we can move on. Sorry.
Good. All right. So the electrolysis of copper to sulfate solution using inert electrodes. Now, since you are familiar with solutions, and I hope you remember that copper sulfate has a formula of CuSO4. So this is, since this is copper 2 sulfate, it is going to give us copper 2 ions. And this is going to give us sulfate negative 2 ions, since they are dissolved into water, and water is going to give us H positive ions and OH negative ions. So this time we're actually facing copper ions against hydrogen ions in case of cations, and sulfate ions versus hydroxide ions in case of anions. Let's talk about copper ions first. Let's talk about cations first. Now, since cations, in case of cations, the reactivity matters. So this is the first place you'd see that they discuss about a phrase reactivity series. What is reactivity series? Are you familiar with it already?
Yeah. The potassium, sodium, that is it that one?
Right, right. So if you look at reactivity series, you'll find hydrogen at the bottom of the series. And below hydrogen, you'll only be able to find a couple of elements more, like copper or silver, or maybe gold, right? All other elements are more reactive than hydrogen and are found on top of hydrogen. Since every positive ion, cation, has to stay in competition with hydrogen ion, since that's the only ion that come out of water, and we're only studying aqueous solutions, so every time hydrogen ion is going to be there as a competitor. So the only ones which are less reactive than hydrogen and would be easier to add electrons to those for a reduction reaction are copper, silver, and gold, which is very easy for a student to memorize. Any other ion in comparison to hydrogen would lose this simple competition and would stay inside the solution. The ion who's less reactive than a hydrogen and won't actually stay inside the solution will quickly run towards the cathode and deposit at the cathode are the only ones copper, silver, and gold. So it's pretty easy to remember, right? And in this case, like in this case, copper is less reactive than hydrogen. So copper ions tend to move towards the cathode. They go towards the cathode, gain the electron over here in a reduction reaction, and are converted into copper atoms. So the cathode is actually coated with a pink brown copper. Whether you call it red brown copper, whether you call it pink brown color, both shades are acceptable at this level. So the pink brown copper is deposited on the cathode. Easy, right? Once you get to know about the reactivity series, it's pretty easy to know and remember which elements are beneath hydrogen or less reactive than hydrogen. Just remember those names. For the rest of the metals on the planet, they are probably more reactive than hydrogen, or the question in the exam is going to mention it for you. So it's easier for you to decide that whether it's going to stay inside the solution or it is going to get deposited at the cathode, like copper does. Moving towards the anions. Now this time we have a polyatomic anion, sulfate. In comparison or versus with hydroxide ions, now sulfate and hydroxide ions from water will be attracted to anode, but sulfate ions aren't easy to oxidize since they are big in structure and they are reactive too. So what happens is that you get oxygen from the oxidation of hydroxide ions from water, and the same equation which was present in the previous purple extension work is given over here. So I usually ask my students, you can cram this equation, and this is really going to help you a lot. So this is the oxidation reaction since we have loss of electrons. And there you go, you have it completed. The rest is an alternate way of looking at it. If you don't understand this part, you can go with the alternate way of water getting oxidized to give out oxygen and hydrogen ions. You can do it that way, but I think this one's better. This one's easier to remember. And you are going to face this equation more than this one in the exams, right? That's why I prefer it. So just skipping the alternate way and moving on, if the electrolysis is continued, my bad, if the electrolysis is continued for a longer time, you'd notice that the copper ions go out and get deposited at the cathode. The hydroxide ions are all converted into colorless hydrogen gas. The bubbles are shown in the diagram. What are we left with? We're left with hydrogen ions and sulfate ions. Now we have H positive and we have SO4 negative too. Crossing them over, you get the formula H2SO4. Balancing the equation, since we have two atoms over here, you need to write two over here. Let's erase these. This is the equation that we get, and the same thing is mentioned over here. The solution turns into dilute sulfuric acid. Right? So the electrolysis will then continue for as for dilute hydrochloric sulfuric acid, which is again given below. What happens if we have dilute sulfuric acid in the solution? What happens to its electrolysis? And I hope you remember that I told you we're going to go with solutions for ionic compounds. Then we are also going to consider solutions of acids. We might also consider solutions of alkalis in this chapter. So sulfuric acid solution for electrolysis is actually a solution of an acid, as I told you earlier. All right.
Yeah.
So the reason we keep on stressing the use of inert electrodes in every single heading given in the book, right, is that electrode is made of what they are made of can sometimes affect the products that you get. If they're inert, they're not going to interfere with the products. If they're not inert, they may interfere with your products. So if you use copper electrodes, oxygen gas is not produced at anode, rather the anode gets smaller. And this is the part where he discusses electroplating. This is known as electroplating. In electroplating, we tend not to use inert electrodes. That's the main point of electroplating. But since it's not very well described over here, so I'm going to describe it a little later. In fact, I'm going to keep it for the end of the chapter. When we're done with the whole chapter, then I'll explain electroplating separately, so that you get a better idea. And if there are questions related to electroplating, you won't have a problem doing it in exams, right? So let's move further. Let's see what we have next. And next one is electrolysis of dilute sulfuric acid, again using the inert electrodes. Now in this case, we have a little bit different kind of apparatus. We have the same power supply, the inert electrodes, but we have somewhat of a different class-based structure in which we have very height-based columns or tubes so that we can actually acquire more gases, right? And then there is a collection tube on top, which consists of dilute sulfuric acid. So when the gases keep on forming and we're getting low in terms of amount of the electrolyte over here, which is dilute sulfuric acid solution itself, we'll pour in some more in and we'll continue with the whole experiment, right? Okay, so let's discuss what's written over here. In this case, the positive ions arriving at the cathode are hydrogen ions, both from the acid and from the water. So since they directly start with it, what I tell my students every time, it's better to go with this activity that I do in the start, right? Okay. So this gives you two of these ions, one of this one. This activity is going to list all the ions for you. So it's easier for you to note down all four ions. One of these ions is going to go to cathode. One of these ions is going to go to anode. The rest of the two are going to combine to stay as the final form of the solution. That is what we have been doing previously. Let me scroll a little bit to show you the same thing. Look, there are four ions. One of them goes to cathode, one of them goes to anode. The rest of the two combine to form the final solution. So we have been doing it every single time we are at the end of the electrolysis. What I tend to do is that I do it at the start instead of the end. And at the end, it would work like a check, right? So we have only hydrogen ions
Yeah.
this time. So there is no other
Yeah.
possibility of the product at cathode except forming hydrogen gas, since all the ions are same. We've already compared sulfate and hydroxide, and we already know that sulfate ions are too difficult to oxidize, and only hydroxide ions are going to go to the anode, giving us oxygen gas. Remember, since this wasn't a part of the system already, so that's the only product. Water does not count as a product, since water was already a part of the system. All right. Now, one thing that you're
Yeah.
going to notice in the diagram, which is different from the previous diagrams, is that you'd notice twice as much hydrogen as oxygen. Now, in case when both the gases are produced, this really depends upon the formula. Look at the half equations above. For every 2 electrons that give us a hydrogen molecule, there are 4 released from the hydroxide ones, right?
Yeah.
So 4
Yes.
electrons would produce 2 molecules of hydrogen. You get twice the number of molecules of hydrogen as of oxygen. Not just that, if you take a look at the formula of water, you'd know there are twice the number of hydrogen atoms than that of oxygen atoms. Of course, twice the number of molecules occupy twice the volume. So this height would be double than this height. That's how we know we have twice as much hydrogen than the oxygen. This depends upon number of
Yep. Got it.
electrons. This depends upon this formula. Going with the formula may be complicated sometimes, so it's better to go with the number of electrons in each equation. Whichever equation gives you a more number of electrons for the balanced equation, the other one gets affected in a way that there is more production. Actually, we can safely say it's positively affected, right?
Yeah.
So since we're getting 4
Yeah.
electrons out of it, and 4 electrons are going to give us 2 molecules of hydrogen instead of 1, so we have twice as much hydrogen as oxygen. Actually, when we do this experiment,
Okay.
the amount of hydrogen we obtain is more than twice as much as oxygen. This is because oxygen is more soluble in water than hydrogen. So what happens, some of the oxygen dissolves in water, hydrogen does not dissolve in water, so we get more amount of hydrogen. What we do to stop this happening is to carry out the electrolysis experiment for a few minutes first in order to saturate the water with oxygen, and then we start collecting the gases. This gives much better results, and the results are hydrogen ratio oxygen gases is 2:1, just like shown in the diagram, right? How is hydrogen more soluble in water? Again, a part of chapter number 18.
Okay.
This specific piece of information will be discussed in chapter number 18. Any information related to gases that we usually get as a product of electrolysis, we are going to test those gases in chapter number 18 and discuss which one's soluble, which one's not, and other properties as well. So if this is clear, I'm going to move on, right? Can we?
Yeah, you can move on. Yeah, you can move on. Yeah.
Okay. He also stated the experiment can be used to show that the formula of water is H2O, hence double the volume of hydrogen and single the volume of oxygen in comparison. Now, reactivity series. With inert electrodes and with solution every time, you should be able to work out no matter which compound they can come up with for an aqueous solution, you should be able to get the answer for product at cathode, the product at anode, and finally what happens to the remaining solution. So if a metal is high in the reactivity series, higher than hydrogen, then you get hydrogen instead of the metal. If the metal is below hydrogen, you obtain the metal at cathode, and you'll find only 3 of these below hydrogen. So you can actually memorize these 3 names. Any other name you come up with, or they give you as a part of exam question, you know that's more reactive than hydrogen, so you're definitely going to form hydrogen at cathode. All right. So these 2 points actually concern the product at cathode or cations. This concern anions. Anions are still a little confusing. When we talked about chloride versus OH, we talked about concentration, how concentrated and dilute a simple piece of fat matters. But when we talked about sulfate versus OH, we talked very differently. We said it's difficult to oxidize. How would we know whether any polyatomic ion or whether a single atom ion, we are supposed to look at the concentration, or we are supposed to look at the ease or difficulty of oxidation? So there is a hint. There is a big, great hint over here. If you're working with a solution of halides like chlorides, bromide, or iodide, concentration matters. All right. So if it's a concentrated solution, for chlorides, you're going to get chlorine. Bromides, you're going to get bromine. Iodides, you're going to get iodine. But if you have dilute solution, you're going to get oxygen. With other common negative ions like sulfate, nitrate, hydroxide, other ones like soluble carbonates, phosphates, hydrogen carbonates, it always is hydroxide that wins, gets to the electrodes, and produces oxygen. So all these 3 points, what is the bottom line? Let me tell you the bottom line in terms of both the electrodes. And it's really easy when I tell you the bottom line. At cathode, every time hydrogen forms, except if there is copper, silver, or gold. Hydrogen is the product every single time, apart when these elements are a part of the salt. Right? At anode, oxygen forms at every time, except when there are concentrated chloride, bromide, or iodide ion present. Concentrated, not dilute. If they're dilute, oxygen will form. If you have sulfate, nitrate, carbonate, hydrogen carbonate, phosphate, any other polyatomic negative ion, oxygen would form. So most of the time we end up with hydrogen and oxygen, and there are just a few exceptions for cathode and just a few exceptions, 3 exceptions for cathode, 3 for anode. That's about it. That's how easy the electrolysis of solutions is. But before we can come to this bottom line, before we can come to this great exam tip, we need to understand the background chemistry, we need to understand the observations, we need to understand the reasons. So it's important for you to know the correct product, but along with that, the reason. Why did you get that product, right? Okay, now,
hold on, that's right.
Extension work. This leaves the problem of what you obtain if you have a moderately reactive metal such as zinc. Since zinc and iron are too close to hydrogen, what's going to happen with that? Reasonably concentrated solutions will give you the metal. Very dilute solutions will give you the hydrogen. In between, you'll get both. But at international GCSE, you don't have to worry about these examples. You will not get an example out of zinc and iron in case of solutions. That's the best part of IGCSE. But this extension work is explained over here as a prerequisite to A levels. In A levels, you are going to get examples like these, and you need to go with all 3 scenarios: reasonably concentrated solutions, very dilute solutions, and something in between. But let's not discuss this extension work more, since you will be required to do that for A levels, not for IGCSE. Right?
Yeah.
So this bottom tip actually solves all the solutions for you. The tip for molten was pretty easy. The element on the left goes to the cathode,
Yeah.
the element on the right goes to the anode. And this step for cathode
Anode.
hydrogen, for anode oxygen, with 3 exceptions for cathode and 3 exceptions for anode, makes the whole electrolysis a lot more easier. And you already know how to write or balance the equations. So whether it's observations, whether it's half equations that you're going to write, whether it's the product what you're going to get, I think with a little bit of practice, you can get pretty great at it, getting every single question of yours correct. Right? Let's see we have up what we have up next, whether the chapter is finished, not. Okay, so with these rules, it's pretty easy for you to come up with the name of the product or the half equation at cathode and anode. So there are different aqueous solutions, and you'll see most of the time you get hydrogen. Why? Because potassium is more reactive than hydrogen, magnesium is more reactive than hydrogen, or the solution itself contained hydrogen. Only in the case of copper, you get copper as a product at cathode. At anode, you would mostly form oxygen. Only in the case of concentrated iodide, or bromide solutions, you'll get iodine and bromine. Since this is a table, so that's why the examples are given like this. Otherwise, in case of iodides, you would commonly find the word concentrated or dilute written right before the salt in these cases. But in the cases of sulfate, you won't find any words like concentrated or dilute, since you don't even require these words for sulfates. These words are only required for chlorides, bromide, or iodide. So this piece of information is only for these 3 ions, anions to be exact. Right? So this makes the whole table a lot more easier to understand. The table only consists of the product or in half equations for cathode and anode. Remember, since they are solutions, so there would be a final product of what's left over in the system. So we have hydrogen and iodine over here. So we're going to form KOH as a final solution, the change to electrolyte. We have hydrogen and bromine over here. We're probably going to form magnesium hydroxide as a final change to the solution. We have hydrogen and oxygen over here. So hydrogen and sulfate are going to react to form hydrogen sulfate, which means water is electrolyzed and sulfuric acid remains still over there. That's the best part of this experiment. What I just said can be explained from the diagram. So I'm going to scroll a little bit. I'm going to get back to the diagram where we had this whole thing. Now, if you dilute sulfuric acid and you keep on producing hydrogen over here at the cathode and oxygen over here at the anode, you're actually electrolyzing water. The dilute sulfuric acid will still remain as a part of dilute sulfuric acid over here, since it will not be electrolyzed at any of the electrodes. So the best part about this kind of electrolysis is that water gets electrolyzed, the component remains the same. You can do the same with dilute salts such as dilute NaCl. Imagine for dilute NaCl, hydrogen would form at cathode. This is the product at cathode, right? Since it's dilute, so OH ions would go and produce oxygen at anode. So this is water electrolyzing. What are you left in the solution? NaCl itself. So you never electrolyzed NaCl. That's the best part. In the similar way, you never electrolyzed sulfuric acid itself, you only electrolyzed water. And you might face this fact as a part of questions in Edexcel. Now, I've seen these questions once every 3 to 4 years, so I call them rare, but this is a fact you need to remember. So I'm going to move again to the same portion we were.
This is something I wanted to ask. Although I do understand, to get the whole idea of the answers, can we do past papers on electrolysis?
Sure. Without doing the past papers right after this chapter is not going to help, since you might forget some facts. So in order to keep the facts and in order to get you to practice and you to remember everything that we studied, so it would be a very good idea not to go with the next chapter and to practice it before the next chapter, right? So if you look at this one, you'd see that you form sulfuric acid as an example to this one. Since sulfate ions do not get to any of the electrodes and hydrogen ions are not going to cathode, copper ions are, so you get sulfuric acid over here. So these are the final solutions which are not a part of this table but can come as a part of your exams. Make sure you write those. All right.
Yeah.
So clear enough so far?
Yeah, enough. Yeah, got it.
Are you done writing?
Yes.
Okay, good, good. I'm going to clear it up. What would happen with non-electrolytes? It's pretty simple. For electrolysis to work, there must be some ions. In case of non-electrolytes, either they are in molten form or in solution form, there are no ions. For example, sugar. Sugar has complete molecules. It's a non-electrolyte. It does not undergo an electrolysis. They won't conduct electricity, and electrolysis won't be possible. So for non-electrolytes, something which is in a liquid state but cannot conduct electricity will not be able to undergo electrolysis. However, since we studied the exception is ammonia solution or acids, so acids in ammonia solution do undergo electrolysis. All right. And we have studied electrolysis of acids before. We just studied electrolysis of dilute sulfuric acid. So, you know, the next part of the chapter is all about quantitative electrolysis, but since it's about time, so I think let's stop right here.